I'm a mechanical engineer by my background. I lead complex projects for a new product design and mentor engineering teams for design thinking. And as part of doing so, I think that the simulations should be a basic skill set for any mechanical engineer. Therefore, I've decided to share a few videos to inspire and raise awareness of some of nice free open source tools available for any engineer. There are many tutorials available online for the basic finite element analysis and different tools out there. But I would rather focus on more real life practical problems. Things that would actually most interest me to watch and learn from others. And the first thing that came into my mind is, there's a whole hype about FPVs and drones, and I came across this design. It's a general design. It's a generic design for FPV. It's named MK4. This specific model I downloaded from GrabCad. I will also include link for this model as well. This is model was published by Yolo Aseneo. Thank you. And I will use this model to simulate various cases. So, like every problem that I engage with, first thing is requirements. I need to understand what I'm required for. One of the challenges of these FPVs is with the natural frequency of the system itself. And why is that? Because the motors, they spin, and they spin very fast, and they create vibrations in the chassis. This translates technically into the flight controller. And the flight controller also has its own sensors, which also sensitive to those vibrations, because these are like accelerators, gyros, whatever. It describes here that the idle frequency is about 50 to 60 hertz, and it can go up to 500 hertz. Why is it important for us to know? Because when a system vibrates in its own natural frequency, then it creates resonance. So therefore, this also reflects on, again, going back to the flight controller, on what the flight controller receive from its sensors, and it create interferences. So when we actually flying this thing, and it varies in between different RPMs of the motors, then what happens is it's actually going through a range of frequencies. So we're definitely going to encounter resonating frequencies. But the question is, if we learn these ahead of time, then we can plan for a specific controller that maybe has capabilities to filter those frequencies. Or we can redesign in order to avoid these frequencies. The thing is, at this moment, we are not looking for any ideas of how to redesign the system, but only to use this tool in order to learn how to improve ourselves or select proper electronics. So looking at this problem, the first thing we need to do is to do model analysis, and the second requirement is they need to sustain a certain amount of impact. And for that case, we took sort of an impact profile that represented about 10 Gs at 11 milliseconds, and you can see here the profile itself. And we're gonna use this profile as an impact simulation to analyze the stresses that this impact just drop of the drone. And we use this analysis in order to look for hotspots that we will like to investigate more if there's a possibility for a failure. And I'm careful with what I'm saying because people tend to see analysis as a definite thing. But we need to understand that analysis is being performed in order to learn about the design and validate our design. But it's not a definitive thing. It's a tool that can easily put you in a position of having a very false results without even knowing that. These tools, they need to be used wisely, because not every point that exceeds the material stress is actually a failure point in the analysis. There are some cases of singularity. There are some cases of how we created the constraints. So all of these, they affect the results, and only an expert that knows how he created these constraints knows also how to analyze the results and explain the results. So it's a good thing to bear in mind, that you need to know how to create constraints, and you need to know how to analyze the results, because some results might be misleading. This is important. So one thing that I want to start with is this. I came across this very nice fine element tool. It uses open source solvers, and here's the information about the guy who created this, and the sponsors for this tool. Well, again, I'm not going to make a tutorial about how to use this software in particular, because there are very good tutorials out there, and I very much recommend to go on YouTube and other channels and look for these. Going back to our problem here, one of the reasons Fine Element is a good also educational tool for engineers, I think, it's because I always encourage engineers to simplify the problem. Look for the way how you can take a complicated situation, a complex system, and see how you can simplify it. For you to use this tool as your daily tool for starting conceptual design to complete design, then you need to understand, in terms of design thinking, how to simplify stuff. And this is good thing to bear in mind when you approach an analysis, because most of us, we encounter like big systems. Even this CAD itself is quite a big system, because it has a lot of elements inside. So now, how do we solve this? We simplify the model. We simplify the model as much as we can. We are looking for small features that like these, that can cause us problems, and we start eliminating those features as much as we can. It's an art in a way, because sharp corners can cause you singularities, but also too many curves and curvatures in the CAD itself, it will create you a lot of elements and unnecessary elements. And looking at this design, the first thing I always do is like just looking at it and thinking, okay, so where the force is going to be, where the fix is going to be, and where do I suspect it's going to be like the most interesting area to study, because this leads me to how I'm going to mesh it, because I'm not going to do a high resolution mesh for every part of it. For example, my assumption is that here, most of the loads is not going to be here. It's going to be like due to bending stresses here and here, and this is, maybe it will take some loads, but only like a spread load of the battery, for example. So these areas here are much more interesting than this one. So when I'm going to create the mesh, I'm going to decide what's the element size in order to reduce the computations time. And how I'm going to use it, in this software, it's pretty much easy. I select, well, first of all, I create the mesh. The first part is meshing parameters, and then I'm going to use very simple meshing here, nothing complicated. I'm going to say, let's give me 5mm element, and the minimum element, it will be like 1mm. And let's see what it does. Okay, of course, I did not select the part itself. I need to select the part. Okay, and now, well, the settings were created. Now I will just run through the meshing just for this part. See what happens. Okay, so it created the meshing. Cool. And we see quite decent elements. It's also something that I analyze, looking for maybe missing elements, because it happens sometimes, and especially these open source softwares. Some faces might be missed out. One of nice tools that they have in this software. First of all, I will hide this one because it's already meshed. Is a tool they call geometry analysis. And why is it good? Because when I use it, I get to see what's the minimum element size found in this specific model. Now what I'm looking for is those more interesting areas in the parts of where I would think there will be more concentrated stresses. Then what I would do is I would perform refining of the mesh in these areas. And this is pretty simple. I just select refine, and let's select this edge here and maybe this edge here. And I will select an element size of 0.01 at these areas and create a mesh. We will see other parts meshed because I already did some meshing before. And as you can see, this is highly refined area. If we take, for example, the other side, like another part which is pretty much similar part, you see that there's like a very high, much larger elements as in comparison to this one. So this is the end of part 1. What we did is we prepared the mesh for the next phase, which is the setup for the analysis. For the next part, what we'll do is prepare the analysis and perform a static analysis. And for the last part, the third part of this series, what we'll do is we'll perform the model analysis and impact analysis. If you have any questions or comments, please feel free to leave comments down below or contact me through LinkedIn.